And good morning, everyone. I'm Michael Tai from National Taiwan University. In this talk, I will present to you RollingLight, a system that enables line-of-sight light-to-camera communications. And this is a joint work with Hui Yu, Hao Min, You Lin, and Xin Yi from National Taiwan University, as well as Kate at Academia Sinica. So what is light-to-camera communications? So in such a system, you use LED lights to send out modulated optical signal to carry digital information wirelessly. And you can use a commodity camera, such as the one in your smartphone, to receive the information. And one of the biggest advantages of using a camera as a receiver is you have the ability to perform what we call visual association. So in a group of pixels in a captured image with your human brain or with computer vision techniques, you can actually recognize the object's identity. And with the same group of pixels, you can actually extract information from the pixel values that actually embeds incoming optical signal. And because we are using the same group of pixels, it actually provides a very natural way for you to visually associate those two pieces of information. And in other words, you're telling, you can for sure tell it is this object you're looking at right now that is actually transmitting this piece of information to you. Now, the next keyword is line of sight. But why is line of sight a big deal? So in line of sight scenario, light comes from an object, it goes directly to the camera, right? So in this kind of a scenario, if in an image there are multiple objects transmitting at the same time, it is actually very easy to separate the transmission from them without them interfering with each other. You can just extract information from different image areas. If you also use augmented reality, which basically means you overlay the received information on top of the object in the image, it actually provides a very natural way to present the information to the user. So for example, this is going to be very useful, for example, in the museum. So if you have a lot of display objects, you take out your smartphone, you point your phone at the light, and then your phone can actually overlay additional information about an object on your screen and on top of that object. And on the other hand, in non-line of sight scenarios, light from an object, it bounces off a reflected surface and then goes into the camera. And in this case, because they are all mixed together, visual association is no longer possible. And it also means it requires additional multiplexing techniques for you to separate transmission from different objects. Then that usually also means reduced performance. So now let's talk a little bit about some background information. Cameras, they can be categorized into two different types by the type of shutter that you use. So it's either a global shutter camera or a rolling shutter camera. And a global shutter camera exposes all pixels in the same image at the same time, like this. And for a rolling shutter camera, it actually exposes rows of pixels, row by row. And consecutive rows of pixels are exposed at slightly different time, and there's time difference between them, which is small, but fixed. So if I use a global shutter camera to try to capture an incoming optical signal, the sampling rate of such a system is going to be equal to the frame rate of the receiving camera, which is usually only 30 Hertz, and that is way too low for most applications. If instead you use a rolling shutter camera to capture the incoming optical signal, what's going to happen is because different rows of pixels capture the signal at slightly different time, and suddenly now in the image, the number of samples you can obtain can be as large as the wide resolution of the image, and that's usually around 1,000. So suddenly you increase your sampling rate by a factor of 1,000, and that also means you have the opportunity to increase the bandwidth by 1,000 times. So that's very good. But the main challenge here is that the channel between the light and the rolling shutter camera we just talked about induces significant signal loss, which is a problem I'm going to talk about in the next couple of slides. So one very interesting phenomenon we found out is between exposure durations of consecutive image frames like this, there's a short period of time during which the camera is actually not doing anything. It's idle and not receiving incoming optical signal. So when that happens, if you're still transmitting, then obviously this part of the signal is lost in the channel. And that also means symbols that you transmit is also lost. So idle period results in this channel loss that we're talking about. So in the previous slide, we assumed that the light actually occupies the entire image. But if that is not true, then now, for example, light occupies only a portion of the image, then in addition to the loss caused by the idle period that we just talked about, there are also rows of pixels that cannot capture the incoming optical signal, right? So there's additional signal loss, and it's related to the size of the light. So additional signal loss as well as additional data symbol loss in the process. Now, if the light is actually in a different location, then you still have this loss, but now actually different portions of the signal is lost in the process, because now different rows of pixels cannot capture the incoming optical signal. So now let's take a look at an example. So in this example, you have a light transmitting to different cameras in different smartphones, and they are placed in different locations, so different distances, and also the light occupies different parts in the image. So what's going to happen? For different devices, different cameras, what you are going to have is different loss ratio due to the idle period we just talked about. And because of different distances, you're going to have different additional amount of signal loss due to that. And also because the light occupies different part of the image, you're going to have different part of the signal loss in the channel. So the real challenge here is we want to make sure that one single transmission format transmitting to different cameras at the same time, this transmission can be decoded, can be demodulated correctly by all the devices. So that's our challenge. Now, this slide shows the goal of our system. So we'd like to offer high throughput despite having this loss we just talked about. And also we'd like to offer countermeasures to recover from the signal loss. So that's our goal. How does that work? In this slide, I show a couple of designs in our system, which I will go through one by one in the next part of the presentation. So, first, we would like to create a high throughput modulation resilient to loss. And the solution we come up with is to use high order frequency modulation. So, there are actually two ways to improve the throughput of the system. So one is actually to use very high sample rate. And in this case, every sample is very short. However, in this type of channel we just talked about, it is very likely multiple consecutive samples are going to be lost in the idle period that we just talked about. And it would be very hard to recover from this type of loss. So we take the second possible approach, which is to use high order modulation. However, we want to keep the sample rate to be very low. And in this case, each sample is very long in time. And so now it is less likely a sample is completely lost in the idle gap we just talked about. And hopefully, if only a part of the sample is received, then we still have possibility to successfully decode the transmission. So high order modulation. But how exactly does our frequency modulation work? So the basic idea is like the following. If you transmit low frequency square wave from your light, which basically means you're turning on and off the light at a certain frequency, but in this case it's very low, what you're going to observe in the received image is a stripe pattern with very wide strip. If instead you transmit with very high frequency square wave, then what you're going to observe in the image is very narrow strip. So the basic idea is like the following. At the transmitter, we use signal frequency to represent the data we transmit. And at the receiver, we use the strip width, the width of the strip in the image to try to demodulate the data. But then how exactly can we relate the width of the strip in the image to the transmitted frequency? So now, let's assume in your image you observe a pair of bright and dark strip that has a width of 2W, which means that it occupies 2W rows of pixels. And then that means, okay, since consecutive rows of pixels, they are exposed at a time difference of what we call T sub R there. It's called readout time. So now, how long does it take for it to capture 2 strips of signal? It takes 2W multiply T sub R, this amount of time. And that actually equals the signal duration of the square wave you transmit. And so now, suddenly we have this equation, 2W multiplied T sub R equals to the inverse of the frequency. And that gives us the relation between the strip width and the transmitted frequency. So now we can revise our scheme. The scheme will be like the following. At the transmitter, you select a frequency from a given set of frequencies to represent this amount of data. And at the receiver, you can estimate the frequency using this just described equation. And then by looking at the frequency, you know what kind of a digital information you transmit. To be able to have very high throughput, you need to have a large number of frequencies in that frequency set. And that also means the spacing between frequencies in that set is going to be very small. And that also means you need a very accurate frequency estimation algorithm in our system. So how do we solve the problem? The solution we come up with is to borrow an algorithm originally designed for audio signal processing. And the function of that algorithm is to estimate the fundamental frequency of a piece of audio signal. So using this algorithm, it has a couple of designs that allow us to, for example, handle variable signal lengths. It's still very accurate, and also it can handle non-uniform illuminated surface. Now, the only remaining problem we have is when you have different cameras, this readout period, T sub R, is going to be different. So let's say you transmit the same signal with the same frequency, but you observe in those images captured by different cameras, the strip width is going to be different. So how do we solve this problem? We borrow the idea of channel estimation. So in each packet, we're going to transmit a preamble symbol with known frequency, that's at the beginning of each packet, and then each camera can actually estimate the value of T sub R readout period by looking at the value by using this equation. So now we solve the problem. The next part, I'm going to talk about how our system handled the signal loss. And the first problem is the signal boundary between consecutive data symbols are going to be different for the receiver and the transmitter. And the solution we come up with is called symbol splitter. So now, again, the problem is like the following. The transmitter and receiver, they have different frame rates, right? So in one capture image, you're going to have, then by observing the sequence number you receive after demodulating, and you see if there's a loss, it's very easy to figure out which exact data symbol is lost in the channel. And now the next problem is how do we exactly embed the sequence number into the symbols? So the idea is like the following. This is the given set of frequencies that we're going to use in the modulation, right? So we first divide it into 3 different sets. Each is corresponding to the sequence number you want to transmit. So let's say I want to transmit a data symbol with sequence number 1, then I choose to use the frequencies in the first set. If you want to transmit a data symbol with sequence number 2, you choose to use the frequencies in the second set. So that's how we embed the sequence number, and so on and so forth. And now the third problem is, after we know a data symbol is lost, how do we recover from it? And our solution is to use XOR base. It's very simple, parity. Okay, so the solution is like the following. For every n-1 data symbols, we add one parity symbol. So if there's one symbol lost out of those n symbols, we can still use the other n-1 symbols to recover the lost one. But the big question is, how do we determine the value of n so that the amount of redundancy is appropriate for, for a certain camera or for a set of cameras? So in our paper, we have a way to derive the loss probability, which takes into account different parameters in the system. And with that calculation, now we can come up with the value of n, which determines the level of redundancy that we're going to add to the system. So a little bit information about our implementation. So we have two types of transmitter in our implementation. One is a very flexible development platform which utilizes software-defined radio, USRP, and we also developed a custom front-end board in that system. On the other hand, we also have a system that is closer to real system where we use Arduino makeup board and also a MOSFET module to amplify the signal. And with both types of setup, we're able to drive off-the-shelf LED lights to transmit the signal. And there are also two different types of receiver. One of them is an offline decoding program which takes a video file as the input, and we can decode the message in the light that is captured in the video. And the second type of implementation is an iOS app that runs in real time on the smartphone, and you can obviously decode in real time and know what's the information in the transmission. Now let's look at some evaluation results. The first part, we vary the receiving frame rate while we keep the transmission frame rate fixed at 30 frames per second. And so if we use only roll frequency modulation, as the difference between the transmitting frame rate and the receiving frame rate becomes large, you can see that the throughput falls to 0 due to the signal loss. If you also add symbol splitter to it, then it's a little bit better because now it can cope with the problem of mixed symbol image frame that we just talked about. But it still falls to 0 as the difference between frame rates is larger. Now, if you also add sequence number and parity, you can see that the throughput is restored over a wide range of frame rates, right? So that also means now our system is compatible with a wide range of devices, of cameras, which has different frame rates. Now the next part of the evaluation, we're going to look at the impact of the size of the light, which also has a relation to the distance between the camera and the transmitting light. So if you use only roll frequency modulation, you can see that when the distance between the light and the camera becomes large, or when the LED light has a very small size in the image, the throughput suddenly drops to 0, right, due to the signal loss that we talked about. If you add symbol splitter, it's a little bit better when the distance between the transmitter and the receiver is smaller. The throughput is a little bit higher, but it still falls to 0 at the same point, right? If you also add sequence number and parity, now you can see the throughput is restored even at larger distances and even for smaller light size in the image. So that means our system now is able to support longer distances or smaller light sizes. So related work. There are a number of related works in this area, and one category is screen-to-camera communications, and we're going to hear about them in this session in the next couple of talks too. This type of system requires a screen that has a large number of pixels to transmit, and obviously the application suitable for this type of system is different for our system and for this type of communication system. And there's also a category which is similar to our work, and our work is actually trying to address problems that has not yet been investigated by previous work. For example, previous work mostly do not support continuous general data transmission, and the throughput is often too low to support the application. To conclude my talk, we developed a line-of-sight light-to-camera communication system, and we can enable applications requiring visual association. And we implement RollingLight, which can resolve heterogeneous signal loss issue. And also, we are able to support a wide range of off-the-shelf cameras, such as the one in your smart devices today. And we have shown significant throughput improvement via system implementation and evaluation. So with that, I thank you for listening to my talk, and I'm happy to take any questions you might have. Thank you.